Imagine trying to understand the plot of a really complex, beautifully directed film.
Okay.
But instead of actually sitting down in a theater and, watching the story play out from beginning to end, you're only allowed to look at 3 random still frames from the entire, 2-hour movie.
Right, just a couple of snapshots.
Exactly. Maybe you get one frame from the opening scene, one from somewhere in the middle, and then, one from the climax.
Yeah.
You might be able to guess who the main characters are, and you could probably get a sense of the genre, but you are entirely missing the story. You miss the subtle character arcs, the tension building in the background, all those quiet hidden moments that explain exactly why the characters ended up where they did in that final frame.
And what's fascinating here is that analogy perfectly captures the reality of the embryology laboratory for the last 40 years.
Wait, really? Just snapshots.
Basically, yeah. I mean, we've been trying to understand the most complex, miraculous biological story in existence, which is, the first few days of human life, by looking at 3 or 4 isolated snapshots.
Welcome back. We are so incredibly glad you are here with us for this 11th installment of our Inside the IVF Lab series. This deep dive is titled Time-Lapse Imaging, Watching Embryos Develop in Real Time.
Yes, and if you've been following along on this deliberate journey with us, we've been slowly walking you through the microscopic sanctuary where life begins.
Right. And in our last installment, episode 10, we spent our time looking at those final snapshots. We talked about blastocyst development, how the lab grades the expansion of the embryo, the inner cell mass that becomes the fetus, and the trophectoderm that becomes the placenta.
Yeah, exactly.
But all of it was based on very carefully scheduled static checkpoints.
Right. We were looking at the culmination of the first 5 or 6 days of development.
Yeah.
But we were evaluating them as, distinct, disconnected events. We essentially judged the final frame of the movie without really knowing the plot.
And today, our mission is to completely shift that paradigm. We are moving away from simply asking what the embryo looks like at a given scheduled moment, and we are going to explore the profound question of how it actually arrived there.
Which is a huge shift.
It is. Time-lapse technology takes us from those isolated, static, still frames, and it gives us the entire film. It adds the critical missing dimension of time. And to truly understand why time-lapse is such a, revolutionary leap forward, we have to ground ourselves in the mechanics and the severe limitations of the old way.
Right. And that old way is the traditional method of static morphology assessment.
Okay, so static assessment.
Yeah. For decades, the gold standard in IVF, and what is still practiced in many exceptional clinics around the world today, is checking the embryo once daily.
Just once a day?
Once a day. The embryologist physically removes the culture dish from the incubator, carries it over to a heated microscope stage, and performs a rapid, highly focused visual assessment.
I want to spend some real time exploring those brief seconds under the microscope, because if we don't understand the snapshot, we really won't appreciate the cinema, right?
Definitely.
When that dish comes out of the dark, what exactly is the embryologist scanning for?
Well, it's a very rigid, precise evaluation. First, they are counting the cells. If we're looking at an embryo on day 2 or day 3 of development, we expect a certain number of cells. Yeah. They're looking for 2 or 4 or 8 distinct cells.
Right.
But just counting them isn't enough. They're also looking at the symmetry of those cells.
Symmetry meaning like the size of them?
Exactly.
Oh, yeah.
Biologically, when one cell divides into 2, those 2 resulting cells, the blastomeres, they should be relatively equal in size. It shows an even distribution of the cytoplasm, which is the cellular fluid.
And if they aren't symmetrical, if, say, one is huge and one is tiny?
It's just the cellular machinery that was pulling the cell apart wasn't perfectly aligned, which, often correlates with chromosomal issues or a lower developmental potential.
Okay, that makes sense.
And beyond symmetry, the embryologist is scanning for fragmentation.
Let's drill down into fragmentation, because we hear that word a lot in IVF circles, but mechanically, what is actually happening there?
So during cell division, the cell membrane pinches inward to separate the one cell into 2. Sometimes, instead of a clean break, tiny pieces of the cytoplasm pinch off on their own, forming little membrane-bound bubbles that contain no DNA.
So they're just like empty bubbles.
Pretty much. They're essentially cellular debris trapped inside the shell of the embryo. Now, a small amount of fragmentation is entirely normal and often completely harmless. But if an embryo is highly fragmented, it means it's actively losing critical cellular mass and energy.
Wow. Okay, so cell number, symmetry, and fragmentation. It is an incredibly rigorous visual inspection.
It is.
But looking at this critically, you have to ask, if this snapshot method, this rapid daily check-in, has resulted in literally millions of healthy babies being born all over the world, why fix what isn't broken?
That's a very fair question.
Right. If you're a patient listening to this, you might wonder why the clinic needs a video if the photograph works just fine. What are we actually missing while that embryo is sitting alone in the dark incubator between Tuesday morning and Wednesday morning?
We are missing the behavior.
The behavior. Yeah.
The entire journey between the starting line and the finish line is essentially a black box. When you only look once every 24 hours, you have absolutely no idea if those cells divided smoothly over the course of the afternoon or if they underwent a chaotic, fragmented division at midnight and then somehow managed to reabsorb those fragments and correct themselves just before you took your snapshot the next morning.
It's like checking on a teenager's bedroom once a week.
Yes.
It might be spotless on Sunday morning, but you have no idea if it was an absolute disaster area on Thursday night.
Exactly. You just see the clean room. The transition to continuous observation changes all of that, though. It eliminates the black box. And this is where we define what time-lapse imaging actually is in the context of the IVF lab.
Okay, lay it out for us.
So it's a system that merges two entirely different pieces of equipment. You have a highly specialized incubator and a built-in microscope with a camera system.
Built right in.
Right in. The embryo goes in on day 0, and it stays in. The camera takes repeated high-resolution photographs of each individual embryo at regular intervals, usually like every 5 to 15 minutes. The software then stitches those thousands of images together to create a continuous, reviewable developmental sequence.
So the camera is actually built inside the house.
It is deeply integrated into the environment itself. And this doesn't just tell you that an embryo is at the 8-cell stage on day 3. It tells you exactly when the first cell became 2, down to the minute.
That's incredible.
It really is. It tells you when 2 became 3, when 3 became 4, and exactly how many hours it rested between each of those monumental divisions.
I do want to clarify something for you listening, because this is an important distinction when understanding your own lab reports. In most clinics, time-lapse isn't completely throwing out the old morphological checklist, right?
No, not at all.
It isn't replacing the static assessment, it's adding to it.
Exactly. The final morphology, how that blastocyst physically looks on day 5, remains incredibly predictive. Time-lapse doesn't replace the need to evaluate the inner cell mass or the trophectoderm. It simply adds the rich historical context of how the embryo actually built that structure.
Okay, so we've established that time-lapse gives us a massive increase in visual data, thousands of pictures instead of 3. But here is the piece that feels incredibly counterintuitive to me. Getting all of this extra visual data actually requires less physical interaction with the embryo. You get more by doing less.
And this is perhaps the single most profound biological benefit of the technology, and it's often completely overshadowed by the flashy videos.
Really?
Yeah. To understand this, we need to step into the sanctuary of the incubator and talk about the biology of disturbance.
The biology of disturbance. Okay, I like that. When we talk about the physical reality of the traditional daily checks, we are talking about human hands opening an incubator door, taking a plastic dish out into the ambient air of the laboratory, walking it over to a microscope, looking at it, and then walking it back. That sounds gentle enough to us, but to a developing human embryo.
Right. To an embryo, which at that stage consists of just a handful of microscopic cells, that short journey across the lab bench is a seismic, potentially traumatic event.
Traumatic.
Oh, absolutely. In the human body, early development happens in the dark, tightly regulated, perfectly balanced sanctuary of the fallopian tube in the uterus. The IVF laboratory is engaged in a constant, exhaustive effort to mimic that internal perfection.
So when that dish comes out of the incubator for its daily snapshot, what is actually happening to the embryo on a cellular level, like physically?
3 major critical environmental pillars are immediately threatened: temperature, pH stability, and gas consistency.
Let's start with temperature because it is the most immediate.
Yes. An incubator is held at precisely 37 degrees Celsius, human body temperature. The moment you take that plastic dish out into a room temperature lab, the thermal mass of that tiny drop of culture media begins to cool.
Because it's just a tiny droplet of fluid, so it's going to lose heat incredibly fast.
Exactly. And even a drop of half a degree alters the metabolic machinery inside the cells. During cell division, the cell builds microscopic scaffolding called the mitotic spindle.
Okay, a spindle.
Yeah, and the spindle is made of delicate protein fibers called microtubules, and its job is to physically grab the chromosomes and pull them apart equally into the 2 new cells. These microtubules are highly sensitive to temperature, If the temperature drops, those structural fibers can actually depolymerize, meaning they begin to fray and break apart.
Meaning the ropes pulling the DNA literally snap.
Yes, which leads to chromosomes being left behind or distributed unevenly. It causes genetic chaos
Just from a half-degree drop.
just from that brief cooling. Then we have the second pillar, pH stability. The culture media the embryo sits in, the fluid providing its nutrients, is balanced using a bicarbonate buffer system.
Yeah.
It relies on a specific constant concentration of carbon dioxide gas inside the incubator to maintain the exact pH of the human reproductive tract.
So when you open the incubator door and expose that dish to the ambient air of the laboratory,
The carbon dioxide dissolved in the culture media immediately begins to off-gas into the room air. As the CO2 escapes, the chemical equation shifts and the pH of the fluid rises. It becomes too alkaline.
and an alkaline environment is essentially toxic to a single cell, right?
It is a massive stressor. The embryo cell membranes have these incredibly complex ion channels. When the surrounding fluid becomes alkaline, the embryo has to frantically open those channels and pump hydrogen ions in an attempt to regulate its own internal pH. And pumping those ions requires energy in the form of ATP.
So instead of using its energy to organize its DNA and grow, the embryo is blowing its energy budget just trying to survive the pH spike.
Exactly. It's burning its cellular fuel simply to maintain homeostasis. And finally, we have the third pillar, gas consistency. Many modern incubators use a low oxygen environment, usually around 5% oxygen. This mimics the naturally low oxygen tension inside the female reproductive tract. The ambient air in the laboratory, however, is 20% oxygen.
Which seems like a good thing, right? We need oxygen to live.
For an adult human, yes. For an early-stage embryo, 20% oxygen is toxic. Exposing the embryo to room air creates an influx of reactive oxygen species. These are unstable molecules that can physically tear through cell membranes and damage the DNA itself. This is called oxidative stress.
Wow. The analogy that immediately comes to my mind is baking a highly delicate, incredibly finicky dessert like a souffle.
Oh, that's a perfect analogy.
The recipe explicitly warns you, do not open the oven door. Every time you open that door to check if the souffle is rising, you let the ambient heat out, you change the humidity, you cause a sudden draft, and you risk the entire cellular structure of the dessert just collapsing. Taking an embryo out of the incubator for a static check is exactly like opening the oven door.
It is the perfect mechanical equivalent because the camera in a time-lapse system is built directly into the heated, gas-controlled environment. The embryo is completely spared those environmental fluctuations. Time-lapse incubators function as a sealed sanctuary.
But wait, I want to push back on this a little bit. We are talking about keeping the embryo in the dark, undisturbed. But a time-lapse system involves a camera taking a high-resolution photograph every 5 to 10 minutes for 5 days straight. That requires light. Doesn't flashing a microscope light on a highly sensitive embryo thousands of times cause phototoxicity? Isn't that worse than the temperature drop?
That is a brilliant question, and it was actually one of the primary concerns among scientists when time-lapse was first proposed. Phototoxicity is a real danger. Light energy, particularly in the ultraviolet and blue spectrums, can generate those exact same reactive oxygen species we just talked about.
So how does the technology solve that?
By completely changing the type of light used. Time-lapse systems do not use white, full-spectrum light. They use very specific wavelengths of red or near-infrared light.
Oh, interesting.
Yeah, these longer wavelengths carry significantly less energy and do not penetrate and damage the cellular structures the way shorter wavelengths do. Furthermore, the light isn't left on. The exposure time for each photograph is incredibly brief, often just milliseconds.
So it's just a tiny flash.
A microflash. The cumulative light exposure over 5 days in a modern time-lapse system is actually less than the exposure an embryo would receive during a single 2-minute observation under a traditional brightly lit microscope.
That is fascinating engineering. So the light is essentially harmless. Which brings us to a really profound philosophical point. If we were to totally ignore all the thousands of pictures, if we literally threw the hard drive in the trash and never once looked at the time-lapse footage, the mere act of leaving the embryo alone in that undisturbed box is a massive biological victory.
The biological reality beneath the technology is that uninterrupted culture aligns with the most fundamental mandate of embryology, which is to mimic nature as closely as possible and cause no harm. Every single time an embryo is handled, no matter how gently, there is a microstress. Removing that stress allows the embryo to allocate every ounce of its microscopic energy toward the monumental, exhausting task of organizing its genome and dividing.
We are finally giving them peace and quiet. But of course, the reality is we aren't throwing the hard drive away, we are keeping the footage. And that brings us to what the lab actually does with all that video.
Right, the data analysis.
The embryos are safely undisturbed, the red lights are flashing for milliseconds, and thousands of images are being captured. What is the embryologist actually looking for when they sit down with a cup of coffee to review this footage? This introduces us to a very specific, somewhat intimidating scientific word, morphokinetics.
It sounds incredibly complex, but if we break the word apart, it makes intuitive sense. Morpho refers to morphology, the physical form, shape, and structure of the embryo. Kinetics refers to movement, speed, and timing.
Ah, okay.
So morphokinetics is simply the study of the exact timing and the sequence of physical developmental events. It transforms the static snapshot into a dynamic timeline of life.
So walk us through this morphokinetic timeline. If you are the embryologist watching the footage on your monitor, what are the specific biological milestones you are tracking with your stopwatch?
The timeline begins remarkably early. Before we even get to the first cell division, if we were observing the oocyte, the unfertilized egg itself, we track its final stages of maturation. We can watch its transition from the M1 stage to the fully mature M2 stage.
Let's define those for the listener. What is M1?
M1 stands for metaphase 1. At this stage, the oocyte is still preparing its chromosomes. It hasn't yet shed its extra set of DNA. When it transitions to M2, or metaphase 2, it extrudes a tiny package of excess genetic material called a polar body.
And you can see that on the video.
You can. Seeing that polar body emerge on the time-lapse footage is the visual confirmation that the oocyte is biologically ready to accept a sperm and be fertilized. Once fertilization occurs, the morphokinetic stopwatch truly starts. The very first milestone we track is the time to first cleavage.
The exact moment one cell becomes two.
Exactly. And the rhythm of that division matters tremendously. If an embryo divides too early or struggles and divides much too late, it historically correlates with lower developmental potential. From there, we track the duration it takes to reach the 3-cell stage, the 4-cell stage, the 5-cell, and the 8-cell stage.
So you're logging every single step.
Every single one. We aren't just noting that it happened. We are looking at the resting periods between these divisions. Do they happen in a tight, synchronous, predictable rhythm? Or is the pacing erratic and staggered?
And as the embryo grows past the 8-cell stage, those individual cells start acting collectively, right? The milestones change.
They do. Around day 3 or 4, we watch for the timing of compaction. This is a breathtaking event to watch on time-lapse. The individual, distinct cells begin to blur their boundaries. They express protein molecules called E-cadherins, which act like biological Velcro, zipping the outer membranes of the cells tightly together until the embryo forms a solid, smooth sphere called a morula. We track the exact hour that compaction begins and how long it takes to complete.
And the final hurdle?
The timing of blastulation. This is when the cells begin actively pumping sodium ions into the center of the solid morula. Water follows the sodium, and a fluid-filled cavity begins to balloon outward, expanding the embryo into a blastocyst. We track the moment the cavity first appears and the rate at which it expands.
This is where the absolute aha moment hit me when I was reviewing the research for this deep dive. We talked earlier about how, with the old snapshot method, you pull the dish out on day 5 and you might see a beautiful, perfectly expanded, highly graded blastocyst.
Right.
But with morphokinetics, you realize that 2 blastocysts can sit side by side on day 5, look absolutely identical to the human eye under a microscope, receive the exact same top-tier grade, but their time-lapse footage might reveal they took completely different, potentially chaotic paths to get there.
That is the ultimate revelation of time-lapse imaging. The journey matters just as much as the destination. One of those identical-looking blastocysts might have executed a flawless developmental dance, dividing from 1 cell to 2, 2 to 4, 4 to 8, in a steady metronomic rhythm.
A perfect timeline.
Exactly. But the other blastocyst, the one that looks exactly the same on day 5, might have had a profoundly abnormal, structurally chaotic pass that was completely hidden in the dark between static checks.
What kind of hidden skeletons are in the embryo's closet? What specific abnormalities does the time-lapse camera expose that the daily snapshot misses?
Well, the footage reveals several transient features, events that happen rapidly and then visually resolve themselves before the next daily check. A prime example, and one of the most significant discoveries of time-lapse, is a phenomenon called direct cleavage.
Direct cleavage. Mechanically, what does that look like on the screen?
Normal, Healthy biology dictates that one cell divides into two distinct cells. In direct cleavage, one cell splits directly into three cells simultaneously. Or you might see a perfectly normal two-cell embryo suddenly fracture directly into five cells.
How is that biologically possible? How does one cell split into three?
It goes back to that mitotic spindle we discussed earlier, the internal cellular scaffolding that pulls chromosomes apart.
Right, the bridge.
Normally, the spindle is bipolar. It has two ends pulling in opposite directions. In direct cleavage, the cell forms a multipolar spindle. It might have 3 or 4 ends, ripping the DNA apart in multiple directions at once. It is a massive, catastrophic disruption of the cellular machinery. The resulting 3 cells receive an entirely randomized, uneven distribution of chromosomes.
But the crazy, almost deceptive thing is an embryo that suffers that kind of genetic catastrophe on day 1 can still go on to form a blastocyst by day 5.
Yes, and that is why time-lapse is so crucial. An embryo can undergo direct cleavage, scramble its DNA, and yet still retain enough basal cellular function to continue dividing, eventually compacting and forming a cavity.
That's terrifying.
It is. If you were only using static snapshots, you would look at that day 5 blastocyst, grade it highly, and transfer it, completely unaware that its chaotic history almost guarantees it's genetically abnormal and cannot result in a healthy pregnancy. Time-lapse catches the direct cleavage on tape, allowing the lab to deselect it.
That is wild. It's masking its own trauma. What else do we see? You mentioned reverse cleavage in our notes. That literally sounds like a cell going backward in time.
Visually, it looks exactly like that. Reverse cleavage is when two distinct, separated cells actually merge back together into a single massive cell. Or a cell might pinch off a large fragment and hours later reabsorb that fragment back into its main body.
Wait, I need to understand the mechanism here. How does a cell just swallow another cell back up?
The outer boundary of cell is a lipid bilayer. Think of it like the soap film of a bubble.
Okay, a bubble.
When two cells are sitting next to each other, they normally maintain their separate structural integrity, but in reverse cleavage, the structural proteins maintaining those boundaries fail. The lipid membranes physically touch, melt into one another, and fuse. The two bubbles merge into one.
Oh, wow.
The result is a single giant cell that now contains 2 nuclei and double the amount of normal DNA. It is a biological disaster, but again, an event that might happen at 2 a.m. and completely resolve visually by the 8 South cm snapshot.
And the final red flag we noted is asynchronous timing. We use the analogy of a rowing team where everyone is rowing out of sync.
It's an accurate visual. Normal division should be relatively synchronous. When a 2-cell embryo divides into 4 cells, both of those initial cells should divide at roughly the same time. If one cell divides and the neighboring cell waits 14 hours to divide, that asynchronous rhythm is highly predictive of lower implantation potential.
Let's take the rowing team analogy further into the actual causality. Why is it biologically bad for the embryo if one cell divides late? They still both divided eventually.
Because of cellular communication. Early embryonic cells do not act in total isolation. They communicate constantly. They send chemical signals to one another, and they form physical protein channels called gap junctions to share molecules.
They talk to each other.
Exactly. If one cell is wildly out of sync in its developmental stage, the chemical signals it is sending out are delayed or incorrect. It causes a cascade of miscommunication across the entire embryo, disrupting the coordinated effort required to form a healthy, complex structure like a blastocyst.
If you're a patient listening, this deeply explains a very specific emotional reality of IVF. It explains why your clinic might call you on day 3 and say, you know, the embryo looks okay today, but it did something really unusual yesterday on the time-lapse. They're seeing the direct cleavage. They are seeing the asynchronous rowing.
And this raises a highly important point about how we process this information. We have to be incredibly careful not to panic at every single tiny deviation on the timeline. The interpretation of these morphokinetic events is extraordinarily complex. Not every detected abnormality has the same lethal clinical significance.
Right, because we are dealing with biology, not a microchip. Biology is inherently messy. It makes mistakes and fixes them.
Precisely. Some transient abnormalities, like direct cleavage from 1 to 3 cells, are almost always lethal to the embryo's potential. But others, like a very slight delay in compaction or the reabsorption of a tiny fragment, might just be a temporary biological hiccup that the embryo successfully repairs. The clinical significance of these markers is something the scientific community is constantly reevaluating. We are still learning which behaviors are absolute red flags and which are just the messy variations of normal life.
So let's look at the sheer scale of this. We have moved from looking at an embryo once a day to capturing thousands of images. We have timestamps down to the minute for every division. We are tracking direct cleavage, membrane fusion, and reverse cleavage, the expression of equaterins during compaction. As a human being, as a working embryologist, how on earth do you physically process all of this? If a busy clinic has 300 embryos incubating at once, you are generating an overwhelming, frankly impossible amount of raw data.
You have identified the exact bottleneck of the technology. The human eye and the human brain are incredibly adept at pattern recognition, but an embryologist cannot manually sit and process millions of data points across thousands of hours of video files efficiently. It is biologically impossible.
Right.
And this is precisely why the advent of massive time-lapse data sets naturally, almost inevitably, paved the way for the artificial intelligence revolution inside the IVF laboratory.
The AI revolution. It feels like every single industry in the world is talking about AI right now, often as a buzzword. But in the embryology lab, it actually makes perfect logical sense. You have a captive audience, a standardized environment, and a massive, continuously growing data set of high-resolution images just waiting to be mathematically analyzed.
Time-lapse incubators created the ideal training ground for machine learning. Before continuous observation, algorithms had very little data to work with, just those 3 or 4 static images per embryo. You cannot train a complex neural network on 3 pictures.
No, definitely not.
Time-lapse provided the deep, unbroken, continuous data streams required to teach an AI how to truly see development.
Okay, let's unpack this. What is the AI actually doing when it scans these embryo videos? Because it's not just playing the video on fast forward like we do.
No, it operates at a level of mathematical precision the human eye simply cannot perceive. We can break down what the algorithm is analyzing into 3 main pillars.
Okay, pillar 1.
First, it analyzes microscopic image features. Utilizing convolutional neural networks, the AI scans the texture of the cytoplasm. It measures the exact density of the cells. It calculates the precise thickness of the zona pellucida, which is the protective outer protein shell of the embryo, pixel by microscopic pixel.
It's quantifying things we literally cannot see with our organic eyes.
Correct. Second, it analyzes developmental timing. When a human embryologist watches the tape, they might note that an embryo divided fast or slow. The AI logs the exact millisecond of division and compares that specific timestamp against a vast global database of hundreds of thousands of other embryos, instantly calculating exactly where the specific embryo falls on a statistical bell curve of viability.
And the third pillar.
Complex pattern recognition across massive data sets. An AI model can review the complete morphokinetic timelines of millions of embryos, cross-reference that footage with the ultimate clinical outcome, whether or not those specific embryos resulted in a live birth, and identify incredibly subtle visual or temporal patterns that correlate with success. It is finding correlations that human scientists haven't even thought to look for yet.
The promise here is massive. We talked in previous installments about how human embryo grading is inherently subjective. If you put 3 highly trained embryologists in a room and ask them to grade a complex blastocyst, you might get 3 slightly different answers. One might grade it a B+, one might give it an A-, one might see a flaw the others missed. It depends on their specific training, how much coffee they've had, or how tired their eyes are at the end of a grueling 10-hour shift.
Exactly. Human fatigue is a real factor.
The promise of AI is taking human subjectivity and fatigue completely out of the equation. Right? Could an algorithm give us a perfectly objective, mathematically pure ranking of which embryo is most likely to become a baby?
That is the ultimate holy grail of the technology, and the marketing surrounding these AI algorithms is incredibly persuasive. But this is where we have to step in and temper that technological enthusiasm with harsh scientific reality.
Okay, reality check.
Yes. There are critical, fundamental questions in the embryology community around AI model validity and, most importantly, generalizability.
Generalizability, what does that mean in the context of an IVF lab?
It means asking a crucial question. Does an algorithm trained in one specific environment work accurately when deployed in a completely different environment?
Give me an example.
Let's use a detailed example. Imagine a software company develops a brilliant, highly sophisticated AI model. They train this neural network using millions of hours of time-lapse footage from a massive, highly successful clinic in Tokyo. That Tokyo clinic uses a very specific proprietary brand of culture media. They use a specific brand of incubator, and they serve a specific demographic of patients. The AI learns the exact morphokinetic rhythms, the exact timing of divisions of those specific embryos growing into those exact chemical and environmental conditions.
Okay, that makes sense. The AI is learning the baseline for Tokyo.
Now, that software company sells their algorithm to a clinic in London or Denver. The clinic in Denver uses a completely different chemical formulation for their culture media. The ambient altitude is drastically different, which changes the barometric pressure, which subtly alters the off-gassing rate of CO2, which minutely shifts the pH.
Oh, wow, the altitude, I didn't even think of that.
Exactly. And the patient demographic is entirely different.
Hmm.
The biological reality is that the embryos in Denver might naturally healthily grow at a slightly different morphokinetic pace than the embryos in Tokyo.
Oh, I see where this is going.
If you blindly apply the Tokyo-trained AI to the Denver embryos, the algorithm might flag completely normal, healthy development as abnormal or slow, simply because the timing doesn't perfectly match its rigid training data. The AI doesn't know about barometric pressure or culture media brands. It only knows what it was taught.
Wow. So an AI model is only as good and only as accurate as the specific environment it was trained in. It is not generating a universal biological truth.
Exactly. Biology is exquisitely sensitive to its environment. An AI trained on specific lab conditions might completely fail or generate skewed rankings when applied to a different setup across the world. This is why the scientific community constantly warns about the risk of over-relying on software-derived scores.
You can't just blindly trust the machine.
You really can't. An embryologist cannot simply relinquish their expertise and blindly follow the computer's ranking. They have to deeply understand the limitations, the training data, and the biases of the tool they're using. AI in the IVF lab is a decision support tool. It is not an omniscient oracle.
It is a tool, not an oracle. Which brings us naturally to the great debate, the elephant in the room that we have to address.
Yes, the outcome.
Right. If we step back and look at what we've discussed, we have uninterrupted, perfectly stable incubators. We have high-definition cameras capturing thousands of data points. We have artificial intelligence scanning millions of pixels to calculate morphokinetic trajectories and flag direct cleavage. It is an absolute technological marvel. But does all of this actually lead to more successful pregnancies?
That is the million-dollar question.
If a patient pays the extra fee for time-lapse, do they have a statistically higher chance of taking a baby home? This is where the enthusiasm of the technology meets the hard, cold, sometimes frustrating evidence of clinical trials.
And this is exactly where the scientific community is engaged in rigorous, heated, and ongoing debate. If we look at the evidence impartially, without taking sides, the data is highly complex, highly nuanced, and frequently conflicting.
Let's lay it out clearly. What does the pro-time-lapse data show, and what does the skeptical data show?
Many studies, particularly retrospective studies, which look backward at data that has already been collected, show clear, undeniable advantages in specific clinic settings. They show that clinics utilizing time-lapse incubators and morphokinetic AI algorithms can achieve pregnancy faster, meaning it takes fewer embryo transfers to achieve a positive test. They also frequently show lower miscarriage rates.
And the mechanism behind that lower miscarriage rate makes sense based on what we've learned, right? They are actively deselecting the embryos with hidden genetic chaos, like those that underwent direct cleavage.
Exactly. The biological rationale is incredibly sound. However, we have to contrast that with the results of large, prospective, randomized controlled trials. In the medical community, a randomized controlled trial is the gold standard of evidence. And several of these massive multi-center trials have shown limited or entirely inconsistent improvements in hard clinical outcomes.
Really?
Yeah. When you look at the ultimate, most important metric in IVF, the cumulative live birth rate per patient, some major studies show absolutely no statistically significant difference between patients who had standard static microscopic assessment and those who had advanced time-lapse AI monitoring.
That is so profoundly confusing for a listener and, frankly, incredibly frustrating for a patient trying to make a decision. You hear about this amazing technology. It intuitively makes so much sense. You know, we leave the oven door closed. We get thousands of images. We use supercomputers to avoid abnormal divisions. Why is it so incredibly hard to definitively mathematically prove that this marvel of technology works better than an embryologist with a microscope?
Because in scientific studies evaluating time-lapse, disentangling the variables is a monumental, almost impossible challenge. Think critically about what we're actually testing in these clinics. When a lab installs a $1 million time-lapse system and suddenly their success rates jump by 10%, the scientific method demands, we ask, why did they go up?
Right. What was the actual secret ingredient that moved the needle?
Is it because the embryologists now have morphokinetic video data and can clearly see and discard the embryos with direct cleavage? Or is the improvement solely due to the quiet oven, Did the success rate jump simply because the embryos weren't taken out of the incubator and exposed to devastating temperature drops and pH shifts for 5 consecutive days? Or is it the third variable? Is it the specific AI algorithm they are using that is successfully finding hidden patterns?
So if a study shows a massive benefit, we don't necessarily know if the benefit comes from the expensive camera, the advanced algorithm, or just from having a really good incubator door that keeps the heat locked inside.
Precisely. Separating those three massive variables, uninterrupted environmental culture, morphokinetic visual data, and algorithmic AI scoring, is incredibly difficult in study design. You would have to design a study where embryos are kept in a time-lapse incubator but the cameras are turned off, and compare them to embryos in a time-lapse incubator where the cameras are on to isolate the visual variable. Until we can cleanly separate these factors, the debate over the ultimate clinical utility of the visual data will continue.
I think we also need to be brutally honest about what time-lapse cannot do, because it is very easy to get swept up in the sci-fi nature of watching human cells divide on a 4K monitor.
It is essential to state the limitations clearly to manage expectations. Time-lapse cannot guarantee perfect embryo ranking. It is still fundamentally based on visual observation, not genetic destiny. Crucially, time-lapse cannot confirm chromosomal normality. We call this cloidy status. An embryo can divide with absolute metronomic morphokinetic perfection. It can look utterly flawless on day 5. It can be ranked a 9.9 out of 10 by the AI and still be genetically abnormal.
Wait, really?
Yes.
Yeah.
It can be unemployed, meaning it is fundamentally missing chromosomes or has extra chromosomes, and it will inevitably result in a failed implantation or a miscarriage.
So an embryo can be a beautiful, perfectly timed, structurally flawless empty shell.
Sadly, yes. Visual perfection does not equal genetic perfection. Time-lapse also cannot guarantee implantation, because implantation is a two-way dialogue. It relied on the biological receptivity and immune environment of the uterus just as much as the quality of the embryo, and it certainly cannot guarantee a live birth. The key takeaway here is fundamental to understanding IVF. Seeing more of development is not the same as fully understanding development. Time-lapse adds unprecedented visibility. It adds profound historical context. It adds the wealth of data. It does not add certainty.
Visibility, not certainty. That is a great distillation. I want to shift gears slightly because even while the scientists, the statisticians, and the doctors debate the ultimate impact on live birth rates at massive international conferences, the ground reality is that this technology is already here. It is sitting in clinics all over the world right now, and it is radically, fundamentally changing the day-to-day life of the clinical embryologist.
The operational shift inside the laboratory is profound. Time-lapse changes the foundational workflow of how an embryologist interacts with their patient's embryos.
Walk us through a typical morning. In the old days, prior to time-lapse, you'd come into the lab, take the dishes out of the incubators one by one, look through the microscope, write down a letter grade on a clipboard, and put them back. How does time-lapse physically alter that routine?
Now, the embryologist might start their morning at a dual-monitor computer workstation in the corner of the lab, never actually touching the physical incubator. They pull up the software and review the massive sequences of images that were automatically generated overnight. It radically changes when embryos are assessed. In a traditional lab, you have to check the embryos exactly at 8:00 a.m. to maintain your 24-hour interval. With time-lapse, you can review the 8:00 a.m. footage at noon if the clinic is busy with egg retrievals because the developmental data is safely recorded in timestamp.
Which sounds incredibly convenient and much safer for the embryo.
It is, but it introduces a massive new challenge for the staff, the data burden. Reviewing a continuous 120-hour time-lapse video for a cohort of 10 or 15 embryos belonging to a single patient takes significantly more time and requires vastly more mental focus than a rapid 30-second static check. It also entirely alters clinical documentation. Instead of writing down a single summary letter grade, embryologists are annotating precise, minute-by-minute timestamps for cleavage events, logging transient abnormalities, verifying that the AI correctly identified the cell boundaries, and interpreting complex probability scores.
It sounds like an incredibly steep learning curve. You are taking highly trained biologists and forcing them to become data analysts and video editors overnight.
It requires a massive ongoing shift in staff training. They have to learn to interpret these complex timelines, deeply understand the biological nuances of asynchronous division, and crucially know exactly when to override the AI if they suspect the algorithm has misidentified a piece of cellular debris as a dividing cell. It is a completely new, highly technical skill set layered on top of traditional, tactile embryology.
If you are a patient listening to this and you know your embryos are sitting inside a time-lapse incubator, this completely explains why you might not get a phone call exactly at 8 a.m. sharp anymore. The lab isn't just glancing through a microscope and picking up the phone. They are processing hours of video footage, annotating milestones, and running data models before they call you with an update.
That is exactly right. The laboratory is digesting a massive amount of developmental history to give you the most accurate update possible.
Okay, we are getting toward the end of our time in the incubator today, and before we wrap up, I want to do a rapid myth-busting segment.
Oh, I love these.
Because when a technology like this hits the mainstream and gets heavily marketed by clinics, it tends to get wildly oversimplified. We've compiled 4 major myths about time-lapse based on what patients frequently hear, and I want us to dismantle them based on everything we've explored today.
Let's address them.
Myth number 1. Time-lapse technology tells the embryologist exactly, definitively, which embryo is the absolute best.
The reality is that time-lapse adds a rich, highly detailed layer of information, but it does not eliminate biological uncertainty. It helps rank the embryos based on statistical probability and morphokinetic history, but it does not provide a definitive, guaranteed winner.
Myth number 2. Using a time-lapse incubator automatically means a clinic has more accurate embryo selection and higher overall success rates.
Reality. Better visual observation does not automatically equal better clinical outcomes. A clinic could have the most expensive cameras and all the morphokinetic AI data in the world, but if their underlying foundational culture conditions, their media, their air quality, their temperature control are suboptimal, or if they lack the rigorous training required to actually interpret the video data correctly, their patient outcomes will not magically improve.
Myth number 3, and I see this advertised heavily on social media. Time-lapse is just a premium feature designed to make cute, sped-up videos of embryos to give to patients for their baby books.
While patients absolutely, understandably love receiving those videos, and it is a genuinely beautiful, emotional way to connect them to the hidden microscopic process, the reality is that time-lapse is a profound, deeply serious clinical monitoring tool. The video file sent to the patient is merely a byproduct of a rigorous, exhaustive scientific assessment.
And finally, myth number 4. Time-lapse imaging completely replaces standard, traditional embryo grading.
Reality. It complements morphology. It does not replace it. The final physical structure of the blastocyst, the health of the inner cell mass, and the trophectoderm remains a critical, highly predictive factor. Time-lapse just tells us the complex, hidden story of how that final structure was built.
So what does this all mean when we put the pieces together? When we step back from the AI algorithms, the near-infrared cameras, and the minute-by-minute timestamps, we see that time-lapse imaging changes not just what the laboratory sees, but how the laboratory fundamentally interacts with the very fragile beginning of life. It moves us from being disruptive, intermittent observers to constant, quiet witnesses.
To synthesize our deep dive today, time-lapse technology represents a monumental leap forward in how we culture and evaluate human embryos. It allows these incredibly fragile cells to grow undisturbed in the sealed sanctuary of a closed incubator, protecting their delicate mitotic spindles and cellular energy reserves from the severe stress of environmental temperature and pH fluctuations. Simultaneously, it grants us a continuous, dynamic timeline of their journey.
It's like flipping the lights on.
Exactly. It reveals hidden developmental milestones, exposes transient catastrophic abnormalities like direct cleavage and membrane fusion, and brings the immense analytical power of artificial intelligence into the lab to help process impossible data sets. And yet, even as it radically revolutionizes the workflow of the embryologist, its absolute clinical superiority regarding guaranteed live birth rates remains a topic of rigorous, necessary scientific debate. It is a powerful tool that adds tremendous visibility, but it is not a crystal ball.
It is visibility, not certainty. And that distillation leads us perfectly into our next installment. Because even with all of this incredibly rich morphokinetic data, even with an undisturbed sanctuary, even with AI scoring algorithms crunching millions of pixels to give us probability percentages, and even with beautiful high-definition video, the laboratory eventually has to make a single crucial choice.
The observation phase must inevitably end, and the selection phase must begin.
In our next deep dive, episode 12, we are going to explore exactly that, choosing the embryo selection for transfer. We are going to tease apart how embryologists actually synthesize all of this overwhelming information. How do they weigh the static morphological grade against a slightly abnormal morphokinetic timeline? How do fresh transfer strategies compare to freeze-all strategies? And we will dive deeply into the profoundly probabilistic, sometimes agonizing nature of choosing the one embryo to transfer. It is the moment where all the abstract science we've discussed so far meets the ultimate, life-changing clinical decision.
It is the apex of the process, where theoretical data becomes practical application.
We want to thank you, as always, for joining us on this deliberate, in-depth journey into the incubator today. We know we get heavy into the weeds of the cellular biology, the mechanisms, and the science, but we deeply believe that understanding the how and the why makes this entire process so much more profound and empowering, especially if you are navigating it yourself.
Thank you for your curiosity, your attention, and your time.
We'll leave you with a final, lingering thought to ponder until we meet again for episode 12. Think deeply about this. If we possess the incredible technological capability to watch the first few days of human life unfold frame by frame, continuously assisted by advanced supercomputers analyzing millions of microscopic data points, and we still cannot predict with absolute 100% certainty which embryo will become a child, what does that tell us about the inherent wild and beautiful unpredictability of biology itself? Until next time.